Everyone can see my screen, right?
Yes.
Okay.
Mm.
Okay. Please all go on mute. Everyone except me. Thank you. Uh, Hello everyone. My name is Revant, and we are discussing about a paper presentation on generative pre-training from Pixel. This is our topic now for a paper presentation. Uh, we are from Advanced Artificial Intelligence class from Zipping Glue professor, and our group is five. Our group number is five, and these are our following. These are our teammates which are involved in this paper presentation. My name Revant Reddy Devana and Umesh Reddy, Vishnu Pada, and Sri Vikas Darshak Venkat Reddy, Nagesh Rao. And from now on, I'm gonna pass it to Umesh. He's gonna explain it from the abstract. Umesh, you
Mm.
can go on.
Yeah. Yeah. Hello, everyone. Let's start with abstract. The generative pre-training from pixels. So, what does generative pre-training meaning? It means it actually it's a deep learning technique which involves in training a new language model in an unsupervised manner. Actually, it presents a novel way to training generative models for a picture synthesis. And also, the author of who written generative pre-training model, like using a pre-training model on a large data set of pictures. For example, Chiffer 10, it is used to purpose in a variation of a file transfer architecture. And also, this pre-trained model is fine-tuned on a smaller dataset for specific image synthesis. And also, the author shows that their model beats previous approaches on various benchmarks, including the prominent COCO dataset. Overall, the article proposes a potential new approach for training generative models at a scale equivalent to GPT-2, which might have implications in numerous domains such as computer vision and graphics. So moving on to the next slide, introduction part. So this unsupervised pre-training was crucial in the comeback of deep learning. So beginning in the mid 2000s, these techniques was the deep belief network and denoising autoencoder where they are widely utilized in neural networks for computer vision. And also, uh, I mean, they were developments such as piecewise linear activation function, which enhance initialization and normalization procedures. And they were eliminated the requirement for pre-training in order to produce a significant results. Several studies question the merits of deep unsupervised representation, which they report that great results with a single layer of learn. And also, like since the state of the art increasingly depend on explicitly incorporating, and also this retrospective investigation of unsupervised pre-training found that it might potentially be determined and also to perform in a current context. And on the other hand, after early good results, it has advanced the state of the art in natural processing language on the majority of workloads. Surprisingly, the training goal of a domining technique such as BERT, BERT, the production of damage inputs is quite similar to that of uh, denoising autoencoder, which was initially created for pictures. So moving on to the next slide. We re-examine generative pre-training on images and show that when using a flexible architecture, a tractable and effective livelihood-based training objective and significant computer resources. For example, it given as 2048 TPU course with generative pre-training is competitive, and also this is especially encouraging because our design employs a connection pattern that is able to match and even exceed techniques that encode 2D spatial structures of pictures. And and also we provide a collection of tests that characterize the performance of our tech methodology over a wide range of data sets. And also we also carry out a number of tests to better understand how well these models have performed. We also look at how well linear probes work as a function of model depth and how scaling the resolution and parameter code which encounters of a technique influences. So moving on to next slide. So next slide is about motivation and significations. Like we investigate both auto-regressive and bed objective using the pre-training. And also we anticipate pixels rather than linguistic tokens using the sequence. Like transformer architecture, like beyond adjusting for picture characterization, it is one method of gauging the quality of a representation. When combined with early halting, pre-training might also be seen as a regularizer or as a good initiation. This model is used as a feature extractor in another method for evaluating the quality of a representation. In specifically, the model is applied to X to yield features of fx given label instance graph of x comma y. A linear classifier is then trained on the data. The assumption the appropriate characteristics should linearly differentiate the classes of transfer tasks. During fine tuning, one model may perform better than another model due to its design. And also in the context of pictures, we first define the auto-regressive and bread goals in this section. We next go over to the specifies of how our transformer decoder will be implemented. So moving on to next slide. See, in this slide, we can see the formulas. Like, for example, we have to consider the high dimensional data x is equal to x1 to x to the n, where we can see in the first formula that p of x is equal to n is equal to 1 n, where p x is equal to x is x1 to xn. And also we choose the entity permutation commonly referred to as a raster order, which is I is equal to 1. And also we can see in the last formula that moreover we take into account that bird goal which samples a subsequence of the form m with a chance of 0.15 for each index, and we refer to m as a bird mask, and we train our model by minimizing the negative log likelihood of the masked elements and m conditional on the unmasked elements x to x1 comma n that we clearly observed in the third formula. And also we choose between lar and lbat and and we try to minimize the loss across our pre-training data set. So moving on to next slide, we see the fine-tuning formulas. See here, f of l represents to fine-tuning, and we pull n comma l and average, and we also do average it throughout the subsequent dimension that we clearly observed in the first formula. And also with the purpose of minimizing a cross entropy, we learn a projection from FL to class logics. And also we discover empirically that the combined aim is LGN plus LCLF, where even more effective is LGen, LAR and LBERT, and also that were comparable, they're comparable in the year 2018. So moving on to next slide. These pictures, we can see the pictures here. Which it is an overview of our approach. We first pre-processing the raw images by resizing to a low resolution and also reshaping into it a one-dimensional sequence. We then choose one of two pre-training objectives where they will be auto regressive, and also there were mask pixel predictions Finally, we evaluate the representation learned by these objectives with linear problem of the fine tuning. So moving on to next slide, paper proposal, which was Raven will take care of this next slides. Mike, Mike on.
Revant, you're on mute.
Mike, Raven, Mike.
Okay. Sorry. Yeah, thank you, Umesh, for passing on it to me. Okay, now we are going to discuss about a paper proposal. Okay, paper proposal. Here, the framework is, despite the fact that supervised pre-training is the most used paradigm for image classification, collecting huge data sets of labeled images is expensive and time consuming. Instead of scaling up labeling efforts even more, we might aim to learn general purpose representations from the much bigger pool of accessible unlabeled pictures and then fine tune them for categorization using ImageNet as stand-in for sizable unlabeled corpus and tiny traditional labeled databases or something similar to CIFAR 10 and CIFAR 100 and STL 10 as stands in for downstream tasks. We study this situation. We employ an extra 1,000 million unlabeled online photos for our biggest model, which are filtered to be comparably to ImageNet. Uh, Unsupervised and self-supervised pre-training can still be advantageous in terms of data efficiency or speed of fine-tuning even when labels are present. Through pre-training without labels followed by linear probing or fine-tuning with labels, we studied this situation. Collection of data and enhanced data. The ILSV RC 2012 validation set serves as our test set. These are the test sets we have taken, and we employ a portion of the ImageNet training data set, 4%, as our experimental validation set. Instead, we divided 10% of the training set into the CFAR 10 and CFAR 100 and STL 10 sets tests. In STL 10, a subset of ImageNet, we are given some unlabeled instances which are disregard. Pre-training on online pictures doesn't include any data augmentation, whereas pre-training or fine-tuning on ImageNet does involve a minimal amount of data augmentation. In particular, while using a data augmentation, we randomly resize a picture so that the shorter side length is between this much, and then randomly crop it to 224 by 224. We adjust the image such that the shorter side length is 224 and utilize a single 224 center crop when accessing on ImageNet. We employ the wide residential network popularized augmentation for CFAR 100 and CFAR 10. Fully network fine tuning. A crop of 32 by 32 pixel is randomly picked from the padded picture or its horizontal flip after reflection padding of 4 pixel is applied to each side. Then coming to the next slide, there is a background diminishment. We must apply additional ways to decrease context length since the memory requirement of the transformer decoder grow quadratically with context length when utilizing the dense attention. If we trained a transformer naively on a sequence of length 2242 on 3, or our attention logits would be 10 of thousands of larger times than those used in the language model, and even a single layer would be too huge to fit on the GPU. To address this, we first downsize our image to a smaller resolution, which refer to as an input resolution. Our model has IR values of these are the values which our model has. An IR value of 322 and 3 is still fairly computationally demanding, while working at the even lower resolution is appealing. Previous researchers have shown that the human ability on picture categorization tends to decline significantly below this size. Alternatively, inspired by early color display plates, we design our own 9-bit color plate by grouping pixel values using k-means with k equals to this value. Utilizing his plate result in unit input sequence length that is 3 times less than the normal RGB plate, which while encoding color properly. So the reduction violates the color channels permutations invariance, but that retains the models spatially invariant. Then coming to the prototype, our model, our most complex model, IGPT XL has where L equals to 60 layers and D equals to this much value, embedding size for a total of 6.B parameters. Our next biggest model, IGPT-L, is almost identical to the GPT-2 in terms of L equals to 48 layers, but has slightly smaller embedding size of D equals to 1536 when compared to this. This is small. For the total of 1.4 parameters, we utilize the identical model code as GPT-2, except that we initialize weights in the layer dependent manner of space transformer and zero initialize all logit projections. To investigate the influence of model capacity on representation quality in generative model, we additionally train IGPT-M, a 455M parameter model with L equals to 36 and D equals to this value, and IGPT-S a 76M parameter model with L equals to 24. These are the values we are taking. And experimental and results, experiments and results. We begin with this is a following graph which we have done with CFAR 10, 100 and STL10. So these are the following results we have gone. In this figure, the quality of the representation is determined by the layer from which features are extracted. In contrast to supervised model, the best representation for these generative models are found in the network centers. We demonstrate this uni-model reliance on depth by displaying the linear probes for the following figure shows everything. And when using a generative pre-training, it is not always clear if a task such as a pixel protection is permanent to picture classification. This shows that the last layer of a model trained for a pixel protection might not yield to the best representation for classification, in contrast to deep auto-regressive generative model, which has the same breadth and the connection pattern throughout every layer. Latent variable models like VAES can avoid this problem by explicitly learning a presentation of the input data. A generative model, many levels are the candidate representation in our first experiment, which examines how representation quality varies throughout these layers. We see a total different pattern from supervised learning. Representations initially become better as function of depth, and then starting around the middle layer, things start to go worse until the last layer. This trend may indicate there are two phases to how these generative models work. Each point gets data from the area around it during the first stage in order to create a more comprehensive visual representation. The consolidation information is used in the second phase to resolve the conditional next pixel protection problem. This could reflect the behavior of the encoder-decoder architecture, which are the ubiquitous in deep learning, but which are trained on monolithic design. Thus, it is critical to look for the optimum layer, which SSU generative model with a linear probe for CFAR 10, adding the last layer reduces performance by 2.4%, which represents the difference between a baseline and the state-of-the-art results. We discovered the presentation qualities dependencies on depth is firmly uni-model across all the contexts. More effective generative model. So this graph shows the relationship between the representation quality and validation of generating loss. Okay, this x-axis represents the validation loss and y-axis represents the linear probe accuracy. As you can see here, IGPT-S has this indicates blue, since this has a less comparatively less when with this one GM and less L. This comes to orange. This indicates IGPT-M. This shows a better improvement than this one. And when compared to GPL, since it uses a large value, you will be getting a better pixel quality here for generative models. As you can see, everything in the graph. So the same thing, this figure demonstrates how linear probe accuracy grows when validation loss on the autoregressive objective lowers throughout the course of training. This pattern is consistent over a range of model capacities, with the better validation losses being achieved by the models with the greater capacities. This emphasizes how crucial scale is to our strategy. Remember that larger model perform better for a given validation loss value. This is the following values which we have got for the following CIFAR 10, which we have taken CIFAR 100 and STL 10, utilizing the unsupervised ImageNet transfer or supervised ImageNet transfer. We are comparing the linear probe accuracies between our model and state-of-the-art model. Linear probes on the STL and CIFAR. The test is learned representatives in the contrast to the models developed at the normal range, which could undergo distribution shock during the linear assessment. Our model was trained the same input resolution. Contrarily, when we downsample to 322.3 before linear probing, we still outperform AMDIM and unsupervised and self-supervised linear on ImageNet. The first improvement is to boost MR while adhering accelerator memory restrictions with I obtain a 65%.2 and achieve a best layer accuracy of 68.7 with an MR of 642. These are the following prediction when compared to this is a comparison between auto regression pre-training and best during a pre-training. These are the strength and limitation are proposed to the methodologies, and as we have discussed everything here, you can check out here. And when coming to the conclusion, according to our finding, learning high quality is unsupervised picture representation. So finally, I'm gonna study this one. Okay. Finally, our conclusions, which combine to those of paper 2019, recommended re-examining the representation learning capacities. Okay. These are the references we have followed for preparing the paper presentation. Thank you. Thank you, guys. We are done with this paper presentation. These are the formulas we are using, fine-tuning and pre-training. Our strategy consisting like pre-training and I think we are up to here. We are good with it. Thank you, everyone.
Yeah, thank you.
Thank you.
Someone can stop the recording. Hello.